Assalamualaikum and hello. In this video, we will present our study and research project titled Numerical Analysis of Modified Susceptible Infected Remove SIR Model for COVID-19 Data using Runge Kutta method. Our research group consists of 3 members. The study is supervised by Dr. Nur Azni Shahari.
We will start the presentation with the introduction of the study. The COVID-19 was first reported in Wuhan, China on December 2019. The disease is called coronavirus and the virus is called Severe Acute Respiratory Syndrome Coronavirus 2 or SARS-CoV-2. The World Health Organization (WHO) announced COVID-19 as a public health emergency of international concern. The first case that was reported in Malaysia was on 25th January 2020 involving 3 tourists from Wuhan. After that, the number of cases kept increasing. The compartmental model is a general model that has been used to apply in modeling infectious diseases. The most common compartmental model is the susceptible infected remove SIR model. This model can be modified with adding new variables and parameters that will affect the pattern of the spreading. Some examples of modified SIR model are SIRD, SIS, and SIRV model. We need to use numerical model in order to compute the SIR model. In the study of Hossein, Mia, and Hossein in 2020, they used Euler and Runge Kutta method to predict the outbreak of Ebola virus disease using SIR model. Based on their study, Runge Kutta method gives better correlation since its step size is smaller. The problem statement for this study is that we know that COVID-19 virus is still spreading. Thus, we need to understand and learn about the pattern and the epidemiology of the infection. It can be achieved by using mathematical models such as SIR model. However, the basic SIR model may not be the best model to use as it uses limited variables and parameters. New variables and parameters such as vaccination, quarantine, and expose will affect the behavior of the pandemic. Next, we have 3 main objectives that we need to achieve. The first one is to apply the basic SIR model and the modified SIR model, which is the SIRD and SIRV model, to predict the number of infected population, IT, and the number of removed population, RT. The second objective is to compare and fit the model with the actual data. The last one is to determine the effect of the basic reproduction number, R-naught, on the infected and removed population.
Second chapter is the background theory and literature review. Firstly, this chapter discusses about the 4th order Runge Kutta method, which is also known as RK4. It is one of the classical methods for numerical integration that is used to solve the ordinary differential equation in this study. Next, it also includes the concept of the SIR model, which stands for susceptible, infected, and removed. If we assume that the total population is N, then at the beginning of an epidemic, the entire population is susceptible to the disease. Therefore, other people can also get affected, moving from category ST to category IT. The transmission rate will determine the speed of the virus spreading from one to another, while the recovery rate is connected to the time needed for infected people to recover or die. As time passes, the infected people in category IT will go to the third category RT. The removed population includes those who has recovered from the disease and died from the disease. The SIR model also can be modified with different variables and parameters. SIRD model with added category death, which considers an infected person can either recover from the disease or die due to the infection. The SIRV model with added category vaccination, which makes a huge contribution to the defense against a pandemic disease. The advantage of the SIR model is it is capable of mathematically modeling the viral dynamic of infectious disease. The transmission rate can be calculated by the model to predict the incoming possible outbreak. Lastly, SIR model can be modified by adding new variables to fit the characteristic of the disease. The disadvantage of the SIR model is the model ignores a few variables that are important, which will affect the results, such as quarantine and social distancing. Besides, it will not be suitable for every disease, as new variable may appear at various times, as the basic SIR model only includes a few variables. For the application of SIR model, first research of influenza by Towers, Vogt, Gaze, Zhang, and Fer in 2011, they presented the SIR model to evaluate the efficacy of control strategies through antiviral treatment during an outbreak of influenza. Said and Norani in 2013 proposed the basic SIR model to study the rebreeding value depends on the number of dengue cases in Malaysia and Indonesia. Lastly is the Severe Acute Respiratory System SARS. A study conducted by Turici and Dancin in 2003 applied the SIR model to understand the pattern of the disease. Here are some research of different types of SIR compartment model used for COVID-19 cases. Arifin, Chan, Amaran, and Musa in 2020 applied the basic SIR model to observe the trend of the outbreak in Malaysia. Wong, Juwono, and Chua in 2021 proposed the SIR model with vaccination to stimulate the effectiveness of the vaccine in reducing the spread of COVID-19 cases, while Diego Cacavo presented SIRD model to predict the evolution of the Chinese and Italian COVID-19 outbreak.
Next is the methodology and implementation. Shown is the research framework in conducting this study, starting with selection of models, transforming the models to Runge Kutta method, fitting models to actual data, computing error analysis of the forecasting, finding the equilibrium point and the basic reproduction number, and ends with analyzing the behavior of models using the basic reproduction number. The model that was selected is the basic SIR model, consists of 3 compartments, and it categorized the recovered and death in the same compartment called the removed population. SIRD model is one of the modified SIR compartment model, as it differentiates the number of recovered and death in 2 different compartments. an SIRV model that has the same compartment with the basic SIR model, but with an implementation of a vaccine in the equation. Next is transforming the models to Runge Kutta method. Shown are the nonlinear differential equations of each model that will be transformed to Runge Kutta to fit the models with the actual data, and the numerical equation will be solved by MATLAB. Third step is finding the equilibrium points for the modified SIR compartment models, SIRD and SIRV model. Lastly, in finding the basic reproduction number R-naught is computed to analyze the behavior of models based on different value of R-naught. Comparing the basic SIR model with the actual data, the chosen date was on 13 March until 9th May. This set of date was chosen to observe the effect of MCO that has been imposed on the 18 March 2020. As seen in the figure of infected population, the model predicted the number of cases will increase at the same rate with the actual data until it reaches its peak on 5th April and start to decrease after that date. This shows that the MCO may curb the transmission of the disease. For the removed population, the model predicts it will increase at the same rate with the actual data up until 10th April and predicts that the cases will be slightly lower than the actual data.
Now we will see the comparison of the SIRD model with the actual data. The actual data to fit the model that we use for SIRD model is from 14th April 2021 until 7th June 2021, which the duration of it is 55 days. We choose this date because the number of deaths was increasing dramatically according to the actual data, where we can see a change from 1-digit number to a 3-digit number of death in that duration. As we can see from the graph, the infected population, recovered population and death are increasing same with the actual data that are fitted. At day 40, the actual data for infection population is a bit higher than the model. For the recovered population, the model and the actual data do not have much difference that can be seen from the graph. As for the death, even though the actual data is increasing, but it is much lower than the prediction made by the SIRD model.
Date was chosen to observe the infected and removed cases as several groups of people have received their first and second doses of vaccine from 1st April 2021 to 24th May 2021. Based on the graph, it shows the prediction growth curve of both infected and removed are similarly aligned to the actual data. For the removed cases, the predicted data and the actual data are increasing at the same rate, while for the infected cases, the predicted data is gradually higher than the actual data. The SIRV model predicts the number of removed cases will increase until it reaches the peak of 2.6 million, while infected cases will increase until it reaches approximately 400,000 cases within the same value of R-naught.
The value of R-naught used for this study is when R-naught equals to 2.7 and when R-naught equals to 0.87. The initial value for the population is the same for both values. When R-naught is greater than 1, it can be seen from the figure A, the graph increases drastically up until it reaches the peak, nearly 5,000 on day 7 before decreasing, while when R-naught less than 1, the graph increases up until nearly 10,000 on day 7 before decreasing. Figure B shows the effect of when R-naught is greater than 1 and less than 1 for the removed population. The pattern of the graph for both values is almost the same. However, we can see the difference in the number of removed cases when observed on day 20.
Now we will see the behavior of the pandemic using SIRD model with two different values of basic reproduction number R-naught. One value of R-naught is 0.87, which is lower than 1, and another one is 2.87, which is higher than 1. Both R-naught have the same value of recovery rate and death rate, but different value of transmission rate. Through the graph, we can see a quite different behavior. For the infected population, for R-naught less than 1, it declines gradually until it reaches 0, and for R-naught more than 1, it rises drastically until it reaches the peak of 1,200, which will eventually create a wave of infection before it decreases until it approaches 0. It is actually proven by the computation of the equilibrium point for the infected population for the SIRD model. Both recovered population and death are showing the same pattern, which is increasing. For R-naught more than 1, both recovered population and death are rising dramatically, where for R-naught less than 1, both are still increasing, but the peak value is much lower than R-naught more than 1. It can be concluded that when R-naught more than 1, more people will get infected and will create a wave of pandemic, whereas if R-naught less than 1, the number of infected population will decrease.
Based on the graph, it was shown on the infected graph that R-naught more than 1 is increasing rapidly until 1,600 and continuously decreasing, while R-naught less than 1 is gradually decreasing from 1,000 until it is flattening. In general, the graph for the number of infected people for R-naught more than 1 is higher than R-naught less than 1. This is due to the value of 2.87, which is more than 1. The removed graph that R-naught more than 1 is also rising rapidly from 1,750 until it reaches the highest peak of 7,000, while R-naught less than 1 is gradually increasing until it reaches almost 3,800. The graph shows that when R-naught increases, the number of removed population also increases. In the SIRV model, the removed rate is considered to be equivalent to the death and recovery rate, as the number of deaths is low compared to the total population. Thus, it explains the differences of the curve increment on the graph of removed population.
We will move to the comparison of infected population between SIR, SIRD, and SIRV model. SIR and SIRV model have the same equation to compute the number of infected cases, while SIRD model has a different equation as it includes the death rate. We use the same value for transmission rate and recovery rate so that the value of R-naught will be the same. Based on the graph, SIR and SIRV model are showing a slightly higher curve at the end compared to the SIRD model. This is because vaccination only helps in reducing the severity of the infection, not prevent people from getting the virus. According to Cunningham in 2021, even United Kingdom already achieved herd immunity, but the average new daily cases is still high, roughly 45,000 cases. Thus, it can be proven why the number of infected population for SIRV model did not decrease even though some people already received their vaccination.
We then analyze the error of forecasting for the basic SIR model and the SIRD model. Mean absolute percentage error is used for the calculation to measure how accurate a forecast system is. Smaller value of mean absolute percentage error shows that the model is fit to the data. Based on the table shown, the basic SIR model provides a highly accurate forecasting with the actual data for the infected population and a good forecasting for the removed population. On the other hand, the SIRD model provides a reasonable forecasting for infected population and death. The value for the recovered population is 10.1038, indicating that the model is a good forecasting model with the actual data. The main purpose of this study is to observe the behavior of the COVID-19 outbreak with different types of SIR compartment model. Based on the result, it can be concluded that the basic SIR model and SIRD model can be used for forecasting future cases as the mean absolute percentage error value is small. However, the basic SIR model may be useful at the beginning of the pandemic only as the variable that may affect the spreading, such as the vaccination, has not yet applied. The prediction growth curve for the SIRV model is similarly aligned to the actual data. The result also shows that greater value of R-naught will result in higher infected population. A wave of pandemic may happen as the equilibrium points are higher and longer time needed for a population to recover from the disease. The result shows that the vaccines are not fully effective in preventing people from getting infected.
Based on our study, it is recommended to use the SIR model or the modified SIR model to predict the behavior of the number of cases, to prepare the appropriate steps and precautions to control the infection of infectious disease. With these models, the behavior of the infection can be predicted whether it will increase, decrease, or create a new wave if the current rate of infection remains the same.